So this course is called Fundamentals of Combustion, and this is a fundamental course which can be core or elective depending upon the curriculum, and this covers basic aspects of combustion. So we will basically spend say about 36 hours of lectures in this, and including tutorials and uh, small quizzes and so on. Basically, we will be able to cover a lot of aspects of thermodynamics, then stoichiometry and so on. Let us see that. So, I am Professor V. Raghavan from the Department of Mechanical Engineering, Indian Institute of Technology, Madras. Okay, so these are the course contents. So there are about 13 topics here. So we will first start with fuels. Fuels are the basic species which is very important for our course, that is for combustion and their properties. So we have to first know about the different types of fuels and their properties. Then the second topic will be we will review the basics of thermodynamics, especially with respect to ideal gas and ideal gas mixtures. The third topic will be on stoichiometry. When I say stoichiometry, we need what is the amount of oxidizer required to burn a given amount of fuel. So that is very important. So after knowing about the fuels, we should know how much oxidizer I should supply. So this basically comes after we decide what is the rate at which fuel is fed into a combustion chamber. So once we know that, then along with the fuel, how much oxidizer. So normally if you say air is the oxidizer which is available in atmosphere, it has oxygen, and this oxidizer has to be supplied. So when you want a combustion to take place, we need two species basically. One is called fuel species, another one is called oxidizer species, and how much amount of fuel is decided by the power rating of the combustor. For example, if I say 1 kilowatt or 1 megawatt etc., that is the power which is going to be the thermal power basically, that is going to be generated out of this combustion chamber, and for that this much amount of fuel has to be supplied. So while deciding that, we need to know about how much air has to be supplied to oxidize this fuel. So once the fuel is oxidized, then only the thermal energy will be released. So the study on how to do the calculations for finding the amount of oxygen required is called stoichiometry. That will be the third topic which we will cover. Then okay, so when you burn an amount of fuel in a particular condition, what will be the amount of heat which is released, or what will be the maximum temperature reached in the combustion chamber? These are two important aspects what we require. So that is actually dealt by first law of thermodynamics. It's called chemical thermodynamics, and first law of thermodynamics deals with that. Then okay, what are the products which are formed? See, we know that this is an irreversible reaction. Combustion reactions are irreversible. Fuel species, oxidizer species are going to react, and entirely different set of species called products will be formed. So what are all the products which are formed, and what will be the typical composition? So that will be known by what is called equilibrium. Okay, so for that we need second law of thermodynamics. So the first and second law of thermodynamics will be applied to combustion problems, and that will be dealt as the topic 4. Okay, then now if you as I told you already, we have seen many species here. So fuel, oxidizer, products, lot of products all there. So that means this study on combustion deals with multi-component mixture. So lot of species are participating as a mixture in this particular study. So we need to know mass transfer basics. Okay, one more thing is the fuel need not be in gaseous state always. Fuel can be in liquid state or solid state etc. So the rate at which gases are evolved from these liquid and solid phases are also very important. So that is also very much important to understand how this evaporation or pyrolysis of liquid and solid fuel takes place. So for that also mass transfer basics are very much important. So we will cover upon some aspects of mass transfer basics in this course. Then the rate at which a chemical reaction takes place is very important to understand. So for example, I want to burn a particular amount of fuel within a particular amount of time. Okay, so what should be the length of the combustion chamber I require? So, how fast it burns, that should be decided, correct, before dimensioning the combustion chamber. For that purpose, we need to know what will be the typical rates of the chemical reactions. That will be given by fundamentals of chemical kinetics. So, that is the sixth topic we will be able to see in this course. Okay, now we go for modeling this combustion. So, that is very important. We have to understand what are the governing equations required for modeling the combustion process. So, that will be the seventh topic, which is called governing equations for reacting flows. Okay, so that is, so this is quite different from normal fluid mechanics or heat transfer applications, because we need a lot of other constituting equations and coupling conditions for modeling a reacting flow. So, those aspects will be covered in this particular topic, which is called governing equations for reacting flows. Okay, now these are the fundamental aspects. So, till now we have seen the fundamental aspects, then we will go for applications. So, now we will start studying about what is a flame, what are the modes of combustion, and what is the characteristics of each mode of combustion, and so on. So, for example, if there is a combustion which is taking place and there is a flame zone which is formed. Okay, when the reactants, when I say reactants, I mean fuel and oxidizer. When the reactants are supplied to the combustion zone, before reaching that zone, if they are mixed, then this is obviously called a pre-mixed mode of combustion. Okay, now when they mix only at the flame zone, okay, they are separately fed to the combustion chamber and they mix only at the flame zone, then we get non-premixed. So, these are the two extreme modes of combustion. One is called premixed combustion, where we premix the reactants fuel and oxidizer and a reaction takes place, okay, basically based upon lot of other aspects which we will cover. Okay, now in the other extreme case, the fuel and oxidizer mix, they are not going to be mixed at all and they mix only at the flame zone. So, these two extremes, now we can have lot of conditions in between these. So, this will generate lot of modes of combustion, etc., and the characteristics of each of these modes are studied from topics starting from 8 onwards to say 11. And here we will also cover laminar aspect and turbulent aspect of reacting flows and so on. So, general characteristics of combustion flame, detonation, then laminar flame propagation, so flammability limits, quenching, ignition, etc. So, these are all the aspects which we need to understand when you go and study about these different modes of combustion. These 8 and 9 are the topics which cover with premixed modes of combustion. Then 10 is the topic which actually covers the non-premixed combustion mode. Okay, then 11 covers the turbulent combustion modes basically. Okay, now 12 and 13 are called heterogeneous combustion topics, where you take a liquid droplet, liquid fuel droplet, and analyze how it evaporates and how it burns. Now, please see that till this point we are talking only about the gas phase combustion. Okay, so fuel is in gas phase, oxidizer is in gas phase, so they mix and they burn and so on. So, different modes we have been able to talk about there, but when you go to topic 12, we have a liquid fuel and oxidizer is in gas state. So, now when you want to burn this, the liquid has to convert into vapor and mix with the oxidizer which is in gas phase, and we have to have the again some different modes of combustion can be accomplished based upon how we do it. So, droplet vaporization and combustion will deal with a particular aspect of how a small liquid droplet will evaporate as well as burn. Similarly, for solid fuels, predominantly we have solid fuels. You can give examples straight away as wood, coal, etc., where basically it have a lot of heterogeneous materials. So for example, moisture, liquid moisture will be there. Then we have species, gaseous species which are evolved upon heating this. Then we have fixed carbon content and minerals which will be inert and so on. So, we will focus our attention basically on a carbon particle combustion. So, solid particle, how it combusts, and what are the features, how will you understand the combustion modes and so on. So, these are the 13 topics which we will be covering in this course. So, coming to the reference books and the textbook, I will suggest Stephen Turn's An Introduction to Combustion, Concepts and Applications, McGraw-Hill publication, as the textbook for this course. because actually this covers a lot of fundamental concepts and lot of worked examples and exercises are given in this book. So this will be the book we will follow as a textbook in this course, and a lot of other books have been given referenced here as reference books. For example, Foreman-Williams Combustion Theory, Irwin Glassman's Combustion, H.S. Mukunda's Understanding Combustion, Kenneth Coe's Principle of Combustion, and D.P. Misra's Fundamentals of Combustion, and Combustion Technology by Raghavan. So these are the reference books which we can follow, and the textbook will be Stephen Terns and Introduction to Combustion, Concepts and Applications. Okay, now before going to fuels and the properties, let us first see some terminologies here. First we will take combustion. So combustion is a chemical reaction which involves two species. I told you two species will be there. One is called fuel species, another one is called oxidizer species. So these are the two important species. Together they are called reactant species. So this reaction is a chemical reaction which is quantified as exothermic and oxidation reaction. First of all, an oxidation process should take place. Okay, that means an oxidizer is involved, and this oxidizer is going to oxidize a fuel species. So this fuel and oxidizer together are called reactant species, and it is an oxidation reaction. But while this oxidation reaction occurs, it is also called exothermic, meaning the heat is released from the combustion chamber to the surroundings. So combustion reaction is an exothermic oxidation reaction. Okay, now what to understand about the fuel species in general we can say hydrocarbon species. Okay, so for example, hydrogen is a fuel species. Hydrogen is a very good fuel. Okay, but always hydrogen cannot be used, but typically we get fuels which are called hydrocarbons because they consist of carbon atoms. General mechanical engineering application oriented fuels will contain hydrocarbons. Okay, so that is carbon atoms and hydrogen molecules. Okay, now when you oxidize these hydrocarbon fuels, carbon atom in the fuel is oxidized by the oxygen to form carbon dioxide. Similarly, hydrogen molecule is oxidized to form water vapor. Okay, so now heat is released when these products are formed. Okay, why? Because the fuel and oxidizer, this reactant mixture will have a higher energy level, and the products which are formed CO2, H2O, they are having lower energy level, and this difference in the energy level is given out as heat. So we will see some examples also later for this. And CO2 and H2O which are formed, they are called major products. So when I say major products, that means that there are several other products which are also going to be formed. They can be called minor products. Okay, but the major products are these two, carbon dioxide and water vapor. Okay, so a fuel species predominantly are hydrocarbon species which has carbon and hydrogen. So for example, carbon graphite solid, it can alone be a fuel. Similarly, hydrogen can alone be a fuel, but in nature we get combination of these. So for example, alkanes, methane, ethane, etc., alkenes, alkynes, every type of things we get. Similarly, if you take a liquid fuel, say petrol and diesel, they are mixture of hydrocarbons. So both carbon and hydrogen are available. So they will be oxidized with the oxygen and form CO2 and H2O. So that is the typical reaction which we are going to be seeing later. And as I told you just before, predominantly oxygen is available in atmosphere, so we will supply air as the oxidizer. So in several applications we will supply air as the oxidizer, and oxygen in the air, okay, that will react with the fuel species. Okay, so the predominant reactions, chemical reaction, take place in the gaseous state. So that means that the fuel, if it is in gaseous state, will mix with the oxygen in the air, and we have to supply energy, that is called ignition energy. When you supply this energy, then it will start the reaction process and perform the products as told in the bullet here. There are other reactions. So for example, a liquid fuel, if you take, the liquid fuel has to vaporize, and vapors of liquid should come out and react like mix with the oxygen in the air, and it has to only form the products later. So a liquid cannot burn by itself. There are special cases. I am telling about the general liquid fuels like gasoline, etc. So, if for example, if you have a liquid gasoline and there is no way it is going to vaporize, it cannot react at all. Okay, even if you supply cold oxygen inside, it bubbles through, it is not going to react unless it forms a vapor cloud and the vapor mixes with the air and gaseous phase reactions are possible, then only it can react. Okay. Now, the exception is there in our own application is if you take solid fuel, you have it's a solid fuel is a heterogeneous fuel. For example, solid fuel has some moisture, it has some trapped gases inside, and it has fixed carbon, and finally it has some minerals. So now when you heat up the solid fuel, first the moisture is released, then the volatiles, the trapped gases, they are called volatiles, they release, and the fixed carbon and the mineral which is called ash, they remain. Now when this particle, the char particle, what we call with fixed carbon and ash, together they are called char particle, when they become hot enough, then the oxygen from the ambient will diffuse towards this surface and surface reactions are possible. So that is one of the exceptions, that is called surface reactions with respect to the solid fuels. So that is a heterogeneous combustion. So you have a solid surface on which a gas diffuses and reacts. Other than that, predominantly all other reactions occur only in the gas phase. So gaseous state. Okay. So now fuels can be in any state. So this means that fuels, we can handle any fuel like which is in gas phase, liquid phase and solid phase. So fuels in gas state, gaseous state readily mix with air and react. Okay. So anyway, it should mix in proper proportions. Anything cannot, for any proportion is not allowed. For example, if you have only 1% of fuel and 99% of air, or 99% of fuel and 1% of air, it is not going to. So that is the limit of mixing of these two, which will contribute to burning process. So those things we will cover later. So the thing is, the fuel which are in gaseous state doesn't need any other process before it burns, mixes with air and burns. So it is already it is in gaseous state. So predominant reactions are in gaseous state. So it can very well mix with the air from the ambient and react upon some ignition source and so on. But on the other hand, if you have liquid fuel and solid fuels, they are condensate fuels, you see that the liquid fuel has to be converted into a gaseous fuel by vaporizing that. Evaporation of liquid fuel should occur. Similarly, the gaseous fuel trapped inside the solid fuel has to come out and react. Okay, so that for that you have to heat this. So that is an additional process is involved. For liquid to vaporize, you have to heat it. For solid to give out the trapped gases inside, it has to be heated up. So this extra heating process is required for the condensed fuels, condensate fuels. So then only it will evolve the required gaseous fuels for gaseous phase combustion to take place. So that is the predominant combustion mode. Okay, now let us now see the classifications of fuel and go ahead with that. So fuels basically are classified into two major categories. One is called fossil fuel and another is called synthetic fuel. The fossil fuels basically are naturally occurring fuels. So fossil fuels are formed over several years under the ground. Okay, so due to several processes occurring there. So due to high pressure, high temperature involved under the ground, these fuels are formed. Okay, so basically the vegetations and the whatever animal and the plant which are buried under the ground are transformed over several years due to geological processes and convert into fuels like crude oil or coal and so on. Okay, and now we have to dig up that and take the required fuels. Okay, anyway, we need to process that later, but they are naturally occurred. No, nothing a man should do to make a crude oil or a coal. So it is naturally available, but we have to spend some energy to take it out. And for example, some pre-processing like cleaning and distillation in case of crude oil, cleaning in the case of wood and so on, so that we use it for applications for power plants and so on. Okay, fossil fuels, okay, have to be processed before. This is not made; they are processed. On the other hand, synthetic fuels are man-made. We have to make it. Okay, so we have to take some. For example, if we take biogas, we have to take some animal waste and make a reactor. Put this animal waste into that, do a process and evolve this gas. That means that we have to make it ourselves. So those fuels are called synthetic fuels, and the fossil fuels are naturally occurring fuels. Examples of fossil fuels are petroleum crude oil, natural gas and coal. Natural gas also are that's a gas which is available when you dig out this crude oil and so on. Coal is a solid fuel. So we get all types of fuels from the ground. For example, petroleum crude oil is a liquid state fuel, natural gas is a gas, and we have coal which is solid. So all the three types of fuels are available from the fossil fuels from the ground. Okay, synthetic fuels on the other hand, we have to make it, as I told you. So biogas is the example which involves usage of say animal waste, the solid waste or some plant waste, etc. So fermentation is the process in a particular reactor under particular conditions. We have to do that so that you get biogas. Okay, so the yield of biogas, okay, the composition of biogas, etc., will be dependent upon the source at which it is formed. Okay. Similarly, synthetic gas, it's called syngas also. We use the solid materials like coal, biomass, etc., and subject to some process like gasification and so on, so that you get synthetic gases. Okay. So we have to design the reactor, we have to use these products there, and the sources, not products, sources there, and get the products which are good fuels. Okay, so why we have to generate this? Because the fossil fuels, we cannot depend on fossil fuels for a long time, just because they are already formed and we are trying to just deplete it, use it for our purposes, and the energy demands are increasing all over the world, and while doing so we cannot generate that. Okay, as I told you, it is the fossil fuels are formed over several years, so they cannot be formed at the rate which we use. So that means that we should also try to produce our own fuels with our synthetic fuels like biogas, synthetic gas, biodiesel, etc., which will substitute some part of fossil fuels, or else we will try to just deplete the fossil fuels and find nothing later. Okay. Now, so out of these fuels, basically again you can see that in the synthetic fuels we can generate liquid fuels and gaseous fuels basically. Okay. So normally we don't generate solid fuel from the synthetic processes, we normally try to gasify a solid or gasify a liquid to get a gaseous fuel. Similarly, we will produce from solid to liquid or from gases to liquid fuels, etc. But solid fuels are not generally formed, basically they are available, and for this renewable sources are used. For example, sugarcane bagasse, then corn starch, rice husk, okay, rice straw, wheat straw, etc. So these are all actually plant wastes. Similarly, animal waste like cow dung, etc., can be used to produce these fuels. Okay, predominantly we can see that solid fuels, solid wastes are used to produce gaseous fuels as well as liquid fuels. So vegetable seed is used to extract a vegetable oil, and vegetable oil is processed in a process called trans-esterification to get biodiesel. So you see that you normally get solid materials from plants and animals, etc., and from that we try to process in a suitable reactor to get gaseous fuel or liquid fuels as synthetic fuels. Okay. Now, in many cases we also use the fossil fuel coal, okay, to get the synthetic gas. Why? Because coal burning is not very easy to do. So we actually in the recent years we have gone to what is called clean coal technology. In the clean coal technology, the coal, when you want to use coal which is actually abundantly available, we need to understand how it can be converted into some cleaner fuels. As I told you, the solid fuels are not very clean, they are heterogeneous in nature. Okay, basically because of the mineral content which is called ash, and also because of say sulfur, and also moisture. In several cases moisture also will be high, and so on. So moisture, sulfur, and this ash. These are the things which are making us making the coal or other solid fuels very heterogeneous in nature and also not very clean. So clean coal technology basically allows us to use some processes in which we convert coal into synthetic gas or some liquid fuels, which are much cleaner than coal itself. So since the man-made fuels, we can have lot of choices, but we end up in producing gaseous fuels as well as liquid fuels. Okay. Now coming to the properties, one common property in all the fuels, solid, liquid or gas fuels, is its calorific value or heating value. So, okay, now I want to construct a power plant, say 2 megawatt in nature. So, for that I need to burn some fuel to generate some thermal power. So, thermal power should be higher than the electrical power. Okay. So, 2 megawatts, say let us say 2.5 or 2.6 megawatts of thermal power produced. So, conversion efficiency etc. taken into account, I will produce around 2 megawatts later. So, this thermal power of 2 megawatts is achieved by burning certain amount of fuel. Okay, it may be solid, liquid or gaseous fuel, any fuel. So, for that when I burn 1 kg of fuel, I should know how much energy is coming out. So, that is called calorific value. So, the calorific value is the heat released. So, because combustion reactions are exothermic in nature, that is the heat which is released when 1 kg of the fuel completely burns. Again, there is a efficiency there. See, when I say completely, it's only my wish, but I do not know whether I can normally completely burn anything. It is not easy to burn everything completely, especially when you go for solid fuels. It is not easy to do because there are a lot of challenges in burning that, because of the heterogeneity of the fuel, especially with the ash content and so on. So, if you but what we envisage here is when you try to completely burn it, okay, what is the heat released when you burn 1 kg of fuel? That is defined as the calorific value, so theoretical value. So, now when I design my power plant, I will use the calorific value, but I will also add a efficiency there to calculate. So, when I say if x kg of fuel is required to achieve the power of say 2 megawatts, I will say I will use x into 1.1 or 1.2 times that. Okay. So, x into 1.2 I will burn, so that I will surely reach that power capacity and so on. Okay. Now, when I say calorific value, these are all done in a standard condition. So, there should be some standards for that. I cannot do, see, one can burn in a particular temperature and say this is the value I got. One can burn in a different condition. So, there should be some standard to specify the calorific value. What is the standard? So, that standard is when I maintain the temperature of the reactants at 298 Kelvin and burn this. Okay, in any process you can use and burn this, and products are formed. So, when the products are formed, heat is also released. Now, you try to extract all the heat and cool the products to again to the same temperature of 298. The standard reference temperature is called 298, 25 degrees is the standard reference temperature. When you cool it to 298, cool the products to 298, you will extract the heat from that. So, what is that heat? That is called calorific value. 1 kg of fuel should burn for that. Okay. So, calorific value is one of the important common properties which we have for all the fuels. We should know that. So, you can use devices like bomb calorimeter etc. to measure the calorific value of a particular fuel.